go directly to the subject. So I'm talking about monitoring and control of microwave drying, and this is actually what I'm showing our results from our Marie Curie EU project that finished a few years ago, and these results are us directly from a PhD project of our PhD student Marcia Hosseini, who's currently working in a spin-off company Roxol here in Kuopio. Might be online, so she can also comment after the talk if there are some tricky questions. And I will introduce here how ECT, capacitance tomography, can be used to control microwave drying in industrial scale. And we had nice collaboration here with a couple of companies from Germany, Vötch and Pinta, and then one university, Karlsruhe Institute of Technology, all from Germany. So we all know what is microwave oven. You all have it at home for heating and cooking food, and here we have used a bit bigger microwave oven seen here on the right. It had 18 very effective power or microwave transmitters to heat up the object that goes in here. And in our case, what we did, we had this kind of foam that is used, for example, for insulation material that we wanted to try using this kind of a large microwave oven. And during this foam making process, one step is so-called impregnation. So this piece of foam is immersed in this kind of a liquid tank, including chemicals. And why this is done is, for example, to make these foams fire resistant for the industry or for building industry. Then after this impregnation, this foam goes into this oven. It slides on this kind of a moving belt, so it moves all the time, and these transmitters send high power, and it starts to heat up, and the moisture is removed. And what they want to have after the foam comes out here is a uniform moisture distribution. When it goes in, the moisture percentage is something like 60 to 70%, and when it comes out, it should be homogeneous moisture distribution, let's say between 15 or 20%. And it would be nice to be able to monitor what is the moisture level here and to see actual distribution, not just average moisture levels in each part of the foam. So what we did, or what Marcia did in her work, was to develop this ECT sensor for measuring the moisture distribution. Also, she did a process model of this microwave dryer, and then finally developed the moisture controller. So let's have a look at a bit of the ECT. So we designed this kind of a ECT sensor having 12 electrodes. So how it works in ECT is that you apply voltage one of the electrodes and ground the others, and measure the capacitances between the electrode plates. And you repeat this for each of the electrodes. And then you estimate the permittivity distribution of the foam inside the sensor. And why we decided to use ECT is that permittivity correlates strongly with the moisture distribution, so it's easy to move from permittivity to moisture distribution. Also, ECT doesn't require contact, so the moving foam can slide through the sensor without touching it at all. So here you can see the sensor at work. So here's the foam going to this microwave oven. Here's the sensor that Marcia developed. And here is the actual ECT device from Roxol, company from Kuopio. And then a laptop that does the image reconstruction online actually here. So that was designed, this reconstruction approach, by ourselves. And we did tests with different moisture levels. So we took a piece of foam and moisturized smaller pieces with different levels of moisture and had a look at how this ECT can estimate these distributions. So we did 2D reconstruction of these pieces of foam to see how it works. And it nicely recognizes that, okay, here's higher moisture as it was in this P1, and here it was lower moisture. So it can discern between different moisture levels. And we also put this foam to move with different moisture levels, and it was also able to detect the correct locations and also detect different moisture levels also for moving foam. And next step for designing the controller is that you should know at least to some level how the system or process behaves. And we need a process model. And we had two strategies, physics-based, so actual PDE model, and then system identification. And here you can see the system of coupled two PDEs that can model what happens here. You have the power of the microwave transmitters here. It heats up the foam, so this T here is the temperature, and then starts to reduce this moisture, shown M here. So to model this system, you have to solve this coupled system of PDEs and also actually Maxwell's equations to get this absorbed power to the foam. So it's pretty intense calculation and takes quite a lot of time, and it's not practical in real-time applications. But we did some simulations and were able to actually also create a LQR controller for this case, but not in real experiments, but simulations. And what Marci also did was system identification approach, where you have this kind of input-output set of measurements, and in between you fit a linear model between these input values and output values. So this is kind of a simplified model, not physical model, how this system works. So you put in input values, so these are the power levels of these transmitters of the microwave oven, different types of signals, so different types of power levels, and then the outcome is the moisture level of the foam. So the permittivity distribution that can be then transmitted to moisture level by a certain function. And here's the system model that was fitted to this data measured by Marci, and you can test it then when you kind of train the system with certain set of data, like here. Of course, it should work with different power levels as well. And for example, here we have tested with different types of power levels, and it fits the measured output and the actual simulated output with this linear model, so they fit quite nicely. And here's another example of that one as well. So it works quite okay, and this has been used and can be used in developing different types of controllers. And Marci tested quite a few, and I saw LQR results from here. So couple of controllers that were developed. PI was the simplest one, but actually worked nicely. So here are some results of the experiments. So what happens here, we have a set point so that the moisture or permittivity change is 20%. It starts from 60% moisture level, and when the ECT device has measured the piece of foam, the data goes to the controller, and it sees that, okay, I have to increase the power because the moisture is too high. And by increasing the power to the 60% of the maximum, it starts to gets dry and it reaches the set point. And then at some point you change the set point and our controller sees that, okay, I have to increase the power again. It increases to, let's say, 75% of the maximum. And after a while, it reaches the set point quite nicely. So this works quite okay in experimental case. And here we only controlled so that all the transmitters got one value. So we didn't separately control all the 18 transmitters because that would have been a bit too complicated. So this is a kind of single input, single output, and this output is actually the average moisture level of the whole foam, computed from the estimated distribution. And here's the actual measured moisture output. So it nicely, first it's about 30%, and then it goes to about 15% as required. So it works quite nicely. And then here are some results of the linear Gaussian or linear quadratic Gaussian LQG controller, where we also tested a similar case with a couple of or 3 different set points. This was a bit more unstable, responded a bit quicker perhaps, but the outcome is not quite good as with the simplified or very simple PI control. But with some tuning, so this could be also get to work quite nicely. And then we also tested kind of compared if you don't control or if you control the system. So here is a case where the initial moisture of the foam decreases by 5%, which means that you wouldn't need that much power to keep the set point. So if you control, this controller sees that here, okay, your moisture level of the foam that goes in has decreased a bit. So it changes the power, so it reduces the power and still reaching the required moisture level. Whereas if you don't control it, you keep up. If you have set the predefined power level, you keep the same power and you heat up too much. You use too much power and it dries too much and you consume too much energy. And this is one of the ideas why this controller is pretty important. Okay.
Marko,
yeah.
Oh, great. Go ahead.
That's the final. So I don't go through these conclusions because I basically said everything. So I can thank you all for listening and I can stop here.